Topics for today. We are in our second day on recursion, and we're going to go over two problems today that have very elegant recursive solutions that do not have easy solutions without recursion. So the reason that we're covering recursion is because next week and on actually Thursday, we're going to be talking about trees. And trees have what is called a recursive implementation for many of their algorithms. But you can also do some neat things with recursion in terms of solving other problems. And the two problems we're going to consider today are the TowersOfHanoi problem and Sudoku, both of which are actually games. So games that are puzzles. Both of them are puzzles. And one way that you can solve puzzles, for those of you who have done them, is with backtracking, where you speculatively try some solution with the puzzle, and then if it doesn't work, you back up and you try something else. And that's called backtracking. And it turns out that recursion is very good for implementing backtracking strategies where you try one solution, if it doesn't work, you back out it's like erasing, and you try a different solution until you get to the right one. Okay, so last time, if you remember, we kind of talked about the mechanics of recursion. So let's see, actually this wasn't what I wanted. Let's go to this. Okay, so a recursion means that you were calling yourself. So here A calls itself. And if you remember, what we said is the way that recursion is able to be implemented is that the computer maintains stack frames for each invocation of a function. And each invocation has its own list of local variables and parameters. So when A was initially called with 10 here, and then A called itself with 9. So when A of 9 was called, there were two stack frames for A. One with the parameter I equal 10, and a second one with the parameter I equal 9. And each stack frame also keeps track of where it is in the execution when it calls itself recursively, so that when it returns to that function, it can pick up execution at that point. So by keeping separate stack frames for each invocation of the function, you don't step on each other's local variables. Okay, so a simple example where we had it was factorial, say int n, might have if n equals 0, return 1, else return n times fact of n minus 1. If it did not store, if each invocation did not store its own copy of a local variable, and they all shared this parameter n, then eventually n is going to reach 0, right? And if you shared it, then when you came back to each calling function, n would be what if you were sharing it? What if you shared it, if n was shared among all the function calls? Shouldn't it still be 0 if you share it? That's bad, right? Because it means that your factorial would always return 0, except for this special case where n originally was 0. So you want to make sure that as you call each invocation, that the calling function retains its unique values for its local parameters and for its parameters. So that's what stack frames accomplish. Okay, so that's the way recursion gets implemented by the computer. Then the other thing that we kind of glossed over but is important is that when you do a recursive solution, okay, there needs to be two cases. We call one case the base case, and there can be multiple base cases. But the base case is a known solution, okay? So it's a case where we know the solution. So for example, with 0 factorial, that's the base case. We know that 0 factorial is equal to 1. Okay, it stops the recursion. Okay, then there's the recursive case. Okay, where the solution is composed from one or more recursive calls to smaller problems. So you're always, and a smaller problem is one that's working its way down toward the base case. So that's what factorial did. Factorial, the base case is 0 factorial is equal to 1, and n factorial is equal to n times n minus 1 factorial. So the recursive case is solving itself by calling a smaller problem, namely n minus 1 factorial. And then once we have the solution to n minus 1 factorial, we multiply that solution by n to get the solution. Okay? Another classic example of recursion is the Fibonacci numbers. So the Fibonacci numbers, you can define them one of two ways. I'll say Fibonacci of 0 equals 1, Fibonacci of 1 equals 1. So you have two base cases here. Fibonacci 0 and Fibonacci 1. And then the recursive case is Fibonacci n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2 for n greater than 1. And here it's for n greater than 0. So the Fibonacci one is actually composed of two recursive subcases. One is fib n minus 1 and one is fib n minus 2, and then you compose the solution by adding the results from the two smaller ones together. Okay, so the Fibonacci numbers is an example where you make two recursive calls. Okay, it's important that you have a base case for your recursion, because if you don't, you would end up with an infinite recursion. Okay, if you had a function that looked like this, let's say you had function, we'll call it factorial. Whoops, not function. So let's say you had int fact, int n. Let's say all you did was you returned n times fact of n minus 1. That was your function. This leads to what's called infinite recursion. Okay, it's the analog of an infinite loop. And the reason it's an infinite recursion, can anyone tell me why it's an infinite recursion?
You're just going to go to the negative end.
Yep, you're just going to go, it's going to drop from 0 to minus 1 to minus 2 to minus 3. It's never going to stop. Eventually what will happen is, remember how I told you that the stack comes up and the heap comes down? Eventually what will happen is you'll get so many stack frames that your stack will run into your heap. And when that happens, your program will be aborted. Okay? So we can have fun with it. Show that to you. Okay, so we're going to have int main. We'll call it with fact6, and we'll see what happens. We'll compile it. Segmentation fault, core don't. Okay, eventually what happened is the stack met the heap, and it ran out of memory, and it dumped core. So you need to be careful in your recursive functions that you always have a base case that will stop the recursion. It could be multiple base cases that stop the recursion, like in the Fibonacci. But that's the important lesson, is that the base case, eventually, your aim is that the smaller problems converge toward the base case. And then eventually the problem becomes small enough, it is the base case. You know the solution to the base case, you return it, the recursion ends, and you're able to compute your answer. Okay, so that's the basic of recursion. Now, as Dr. Planck says, you have to be careful with recursion because you can get, let's see, efficiency. There we go. Here's the Fibonacci numbers. If you write a very simple Fibonacci thing and you start to look at what the calls look like, let's do that. Let's do it for Fibonacci 4. So Fib 4 calls what? Fib 3 and Fib 2. Fib 3 calls Fib 2 and Fib 1. Okay, that's a base case for Fib 1, right? But Fib 2 is going to call what? 1 and 0. And Fib 2 calls Fib 1 and Fib 0. So there's a couple issues. First of all, you can see that there's redundant calls here, right? So this and this. So that's inefficient, but if I were to do more things, you would find that there's a lot more duplicated calls here. Like if I did Fib 5, which would call Fib 4 and Fib 3, now Fib 2 is going to get called even more times. So it turns out that with the Fibonacci recursion, there's a lot of duplicated calls. Now, there's something called caching, which we won't do in this course, but you could actually cache the result of a call and then look it up to see whether that call has already been made. But without it, it actually makes the number of calls to Fibonacci exponential. So he actually does write it out. He says, let's count the number of times Fibonacci is called. Okay, so what he's saying is, let the number of times that Fibonacci is called be f of n. Okay, so we know that for f of 0 and for f of 1, we call it once. Okay, so if it's f of n, we know that we have to call f of n minus 1. So it's going to have that many calls to f of n minus 1 and that many calls to f of n minus 2. Plus, we were called once, right? The 1 here is for the call to us. So we were called once. And the call to Fibonacci n minus 1 is going to have that many calls, and the call to f of n minus 2 is going to have that many calls. So this is the number of times fib n gets called. So we can see that f of n is got to be greater than fib of n. Does that make sense? Can someone explain why it has to be greater than fib of n? What's the definition for fib of n? Doesn't this look a lot like the definition for fib of n? What's the difference? Plus 1. What's the plus 1 mean? F of n is greater than fib of n, right? It's 1 greater. Actually, it's worse than that, but it has to be at least 1 greater. I'm seeing some blank looks. Does this not make sense? It is important. If you have a question, don't hesitate to ask. Okay. So we know that f of n must be greater than fib of n. Okay, well, it turns out that fib of n, we're not going to prove it, but it's roughly 1.6 to the n power, which is exponential. It's pretty bad. Okay, you can try it. If you enter 1.6, let's try it with 30. Okay, let's do a calculator and try it with 30. I'm doing it with a scripting. 1.6 to the 30th power is 1,329,228. Okay, so to get the Fibonacci, the 30th Fibonacci number, we're going to make roughly 1.33 million function calls. Just for Fibonacci of 30. That's pretty awful. Okay, let's do it for 40. Okay, now we are up to 146 million. We increased our Fibonacci number from 30 to 40, and we went from 1.3 million to 146 million. Pretty bad. Okay? I don't care how fast your computer is. It's not going to return very quickly from that. Okay? You're going to be waiting for a while. So if you're not careful with recursion, it can bite you. Okay, so you have to be careful about that. And there's a very efficient non-recursive solution to the Fibonacci numbers. Here it is. This is Fibonacci 1 back. This is Fibonacci 2 back. This is the current Fibonacci number. So this is the non-recursive solution. So if n is less than or equal to 1, we return 1. That's the base case. Then otherwise, we know that the first two Fibonacci numbers are 1. And he goes into an infinite loop, always incrementing I by 1. So what he's trying to find is the nth Fibonacci number. So he calculates the current Fibonacci number as the sum of the two previous Fibonacci numbers. If I is equal to n, he's got it, so he returns. Otherwise, he just he moves them up each by 1. So what he's doing is he knows that Fibonacci of 5 is equal to Fibonacci of 4 plus Fibonacci of 3. So after he computes Fibonacci of 5, what he's doing is he is essentially saying that fib im2 is equal to fib 4. What he's saying is fib im1 is equal to fib 5. So he's just sliding his values, in effect, 1 over. And that's a very efficient non-recursive solution. In fact, it takes order n time. So it's an example where the Fibonacci, you can be lulled into the beautiful recursive, whoops, I don't want to capture this. Oh, darn it. Okay. You can be lulled into this beautiful, very elegant function, which will take forever. Or you could write this somewhat ugly function that runs very efficiently. So you need to be careful with recursion. However, when recursion works, it's a thing of beauty. So we're going to consider two puzzles. One is the Tower of Hanoi, and Dr. Plank found this photo on the Swarthmore's website. I'm sure that some of you have seen onion rings that are that big. So the idea, how many have actually heard of Tower of Hanoi before? Raise your hands. How many haven't? That's fine. I hadn't heard of it when I was at your point in school. So here's the deal with Towers of Hanoi. You have 3 spindles, okay, that you can put, and you have rings. Okay, let's see if I can get a good Towers of Hanoi. Okay, so here's the classic thing. So you have 3 rings. Yeah, just show me the photo. Okay, so you have 3 rings. And the idea is you want to move this pile to this spindle, the middle spindle. But in moving it, you can never put a larger ring on top of a smaller ring. You can only put smaller rings on top. So for example, a second, I've been lecturing for a while, so I'm going to get a chair to sit on. So I don't obviously have a Tower of Hanoi set myself. So let's do it this way instead. So we start with some spindles. And let's say that initially, I'm going to make it simple. We just have 3. Okay, so I want to move that pyramid over to this spindle. So one way I can start is to move the smallest one to this one because it's empty. Okay? Now, what I'm not allowed to do, an illegal move, is to move. I can't move this one to right here. That's an illegal move because I put a bigger one on a smaller one. So that's an illegal move. Okay, so the next thing I could do is I could, in fact, this wasn't a very good way to start. Okay, I can move this to here. Actually, it's a fine way to start. So I move this one over to there. Now I can move this one over here. Okay, now I can move this one to here. This is the biggest one. Now what should be my next move?
You put the top one on the very left.
Yes. So the next good move is to put the top one here, this one, and move it over to here. Now what's my next good move? The second biggest one goes to the middle. Good, Mac. Okay. And now what's my final move? Smallest one goes to the top. Okay, so that's the solution. Okay. Now, it may be surprising that you can move an arbitrarily big stack with just 3 spindles, but you always can. Okay, it turns out to have a very elegant solution recursively. If you tried to do this without recursion, you would have a great deal of difficulty. But the recursive solution is very elegant, and that is, if you have the case of a bunch of things here, the idea, and you have 3 spindles, so you want to move it to here. The recursive solution is to move a pyramid with the n-1 smallest items over to here. Okay? Then once you've moved the n-1 over to there, all you have left, I'm kind of being bad, let me make blue be the, I have 1 blue over there. Once I've moved the n-1 pieces over here, I can move the remaining piece over to there. And now I repeat it, moving this n-1 over to here. So the idea with Towers of Hanoi is we move the top n-1 pieces to the rightmost spindle. So the solution is move the top n-1 disks to the rightmost spindle. Then 2, move the bottommost disk to the middle spindle. And finally, move the n-1 disks from the rightmost spindle to the middle spindle. So that's a recursive solution, and it always works. Okay, so that's the solution you can use to solve Towers of Hanoi. And it's recursive because you first solve the problem for the top n-1 disks. Once you have that solution, you move the bottommost disk to the middle spindle, and then in effect, you do it again. So what's the base case for this recursion? What's the smallest one that's interesting? Yes, where you just have 1 disk. So the base case is 1 disk. In that case, it's very simple, right? You just move the disk from the leftmost spindle to the middle. That's the base case. So do we agree that's the easiest case? Okay. So we'll get back to his other stuff first, but the basic solution is right here. So here's the function solve, and you're given a pointer to your towers. So those are the 3 spindles. Conceptually, the towers is a pointer to your 3 spindles. Int is the numeric index of the from spindle, and 2 is the numeric index of the to spindle. So these are your 3 towers, pointer to 3 towers. From is the index of the tower containing the pyramid. 2 is the index of the tower or spindle, sorry, index of the spindle. Index of the spindle to which the pyramid should be moved. And n pieces is the number of discs on the pyramid. Okay? So this is our base case. If the number of pieces is 1, we're going to simply move the piece from the from spindle to the to spindle. So make move simply says to move the top piece. So make move, let's put it over here, make move moves the top disc from spindle from to spindle to. So that's what make move does. Moves the top disc from spindle from to spindle to. So the base case is simple. It's just moving the one piece from the from disk to the to disk, and we're done. The print is just printing out the towers so that we can look at them, the spindles. So we'll return to print in a moment. And then it returns because it's done. So this is the recursive case. Okay, so on the recursive case, I have to do some erasing. Does everyone have down what I already have here because I need to clear the ink? Everyone have it down? Okay. So here's our recursive case. So let's say that what I asked you to do was I'd asked you to move the pieces that this is 0, this is 1, and this is 2. And I asked you from is 1 and 2 is 2. So you're moving from 1 to 2. It means that your free spindle, which Dr. Planck, this is your free spindle. It's your work spindle. Okay, for, let's call it, he calls it other, but I'll call it free spindle or scratch. Let's call it scratch. It's your scratch spindle where you can put stuff, like scratch paper, okay? He calls it other. So basically, what he's doing with his for loop, what this for loop is doing, it's just determining which of the spindles is the scratch spindle. That's all that for loop is doing. Then the solve is doing the 3 steps right here that I told you. Step 1 is to move n-1 pieces. So step 1, move the top n-1 from to. I'm sorry, from to other. So that's moving it to the other or scratch one. Then step 2, move the bottommost piece to 2. And then step 3, move the top n-1 pieces from other to 2. So that's the recursive case. And it's very elegant. There's some print statements in there to print out the towers so that you can see what's happening as the individual moves are made. But that's the basic solution. Okay. The other stuff I'll let you look at, he's just doing some printing. And I'll let you look at the print code. But and we will look at the data structures. Let's just take a look at an actual running of it. So and run it on Towers. Let's see. So we're going to run the tower with 3 pieces. And let's use more too. So we first move 1 down to here. Then you can see we end up, the second step, we move the 2, 1 from tower 0 to tower 2. Then in step 3, we move this onto the top, giving us this solution. Then we move 3 to there, and so on and so forth. So all he's doing is printing out each move. Okay, and you can do it for however many you want. This is the case for 4. So it's just showing you each move. So that his print statements, that's what's going on. As you make each move, he's simply printing out the current state of the spindles. Okay, so if you look at what actually is a tower, here's his .h file. So it's a class. So basically, it's just a class, and his spindles are actually a deque of integers. And he has 3 of them. So each spindle is a deque that is keeping track of the number of pieces that are on it. And he's going to represent his disk as integer. So a disk of size 1 is 1. A disk of size 2 is 2. So if you have a problem where you have 4 disks, what he's going to do is push 1, 2, 3, and 4 onto T of 0. Because initially you want the 4 disks to be on T of 0. So each spindle is a deque. Now, what are the 2 operations that we are actually doing with our, when we move, what are we doing with the piece? We're moving it from one pyramid to another, right? So think about this for a moment. Could you use a vector for this problem? The answer is yes, because we're always removing from the top, right? And we're always adding to the top. So actually, you could do this as a vector. He's using a deque because he's printing out some stuff, and he says that it's easier for him to do his printing if he is using a deque. So if all you cared about was finding a solution without printing the intermediate states, you could use a vector. He's using a deque because it's simpler. Okay, we already saw the solution. Make move is pretty simple. It's going to remove a disk from one deque and move it to the other one. Prints the one I'm not going to bother with because it's just him doing ASCII art. And we don't really have time to go over it. So you can see here's his initialization code. And as I said, he's simply running through his loop from 1 to n, and he's doing a pushback. So by doing the pushback, he is actually putting the smallest disk at the beginning, and he's putting the biggest disk at the end. And he's doing that because it's going to make it easier for him to print. Because when he's printing, he wants to put the smallest disk on top. It's easier for his print routines if the smallest disk is at location 0. So that's why he's doing it with DQs. So make move. He first checks a whole bunch of error checking. He wants to make sure that your spindles are named correctly, that they're not invalid spindles. He wants to make sure that you're not trying to move from an empty spindle. He's trying to make sure that here that the piece isn't too big, that you're not trying to move a bigger piece onto a smaller piece. I'll let you look at it later on your own, but his 4 initial things are just doing error checking. And then the last thing is doing it with the actual move, where he's moving a piece from one tower to the next. So here, he's moving. So you can see that the 2 tower is getting the top item from the from tower, and then he's popping that small item, the smallest item or top item, off of the from. So make move is quite simple. Just pushing the smallest piece onto the from tower, popping it off of the from tower. Okay? And like I say, he does some more complicated, not complicated, but I would say tedious stuff for printing, and we don't really have time to do it. If you find that in going over it you have difficulty, I'll be happy to answer email questions or questions about it in office hours. It is worth going over it to see what he is doing, but I'm not going to cover it. So any questions about Towers of Hanoi? Okay, let's move on in that case to Sudoku. So just out of curiosity, how many of you have seen Sudoku? And how many have not? A couple probably. Anyone has not seen Sudoku? Because if you haven't, I'm not going to go over how to do it. So speak now or hold your peace. Okay, I'm going to assume you know how to do it. Okay, so just a quick review. There has to, a solution means that every number in a row is unique, every number in a column is unique, and every number in a 3x3 panel is unique. And initially, you are given some partial solution, and you have to replace the dashes with numbers. Okay? So a recursive solution to this, which involves backtracking, is to start and put the number 1 in the first square. And to verify, first of all, that that is a valid, would keep it valid. So in order for that to be valid, we need to make sure that what? What are the 3 things we need to check when we set the first square to 1? What do you do when you solve a Sudoku puzzle? Okay, do that again, Max. Say it louder.
Check the row, the column, the panel.
Very good. So you check the row to make sure there's no 1 in it. You check the column to make sure there's no 1 in it. And you check the panel to make sure there's no 1 in it. Those 3 conditions are satisfied. So tentatively, this is a fine solution. Okay? Now we go to the next one. And if we're doing a brute force thing, which we are, we start by trying to put a 1 in there. And immediate, I know, Mac, it's not smart, but we're not trying to have a lot of smarts here. The first thing we do is we try to put a 1 in, and it's no good. Now we try to put a 2 in, and is that any good? Lots of problems, both in the panel and the row, right? Now we try a 3, and good or bad? It's in the row already, so now we try 4. It's in the column. 5. 5's okay, right? So we put a 5 there, and we move on to the next one. And the first number that it will work in there is what? It'll try 1, 2, 3, and then 4, and that will work. Then it will come into here, and it can try 1, which is no good, 2, 3, 4 is no good, 5 is no good, but 6 is a winner, right? Do we agree that 6 could potentially work here? Okay, so we'd put a 6 in there, and you can see here's the final solution. You can see that 6 is ultimately not going to work. Okay, and you can kind of see what's the number we would first try here now? 7, right? But that would force, what is forced into here? 8, and that's no good. So we would backtrack to this point. This is the first backtrack. So we backtrack to here. 7 didn't work. We can put an 8 in here, right? So now this is known, this is known, this is known. So now we would have to put a 7 in here, which is tentatively right. So now we would move on to this row, and eventually we would find out that this solution doesn't work either. I don't know where. I don't want to try all the things. But eventually we would find out that this solution doesn't work. So we would have to backtrack all the way. Well, let's try it. 7. The first number that works here is a 3. So then we would probably put a 4 here. We'd try to put a 5 here, then a, nope. We would put a 1 here. No, we can't put a 1. 2. 2 would be the first one we would try. At some point, we're going to end up having to backtrack all the way to right here. Okay? If 7 doesn't work, 8 and 9 don't work either, right? Do we agree that if 7 doesn't work here, 8 and 9 don't work either? Yes? So now we have to move all the way back to here, and we would try to put a 9 in here. But a 9 doesn't work in here, right? So we'd backtrack all the way to here, and we'd have to put an 8. So that's the idea. Is I know this is not how you would solve it. You would solve it more intelligently. But this is what is called a brute force backtracking algorithm, where we go to the next empty or unfilled in place, and we fill it in with the next valid number, and then we move to the next square. And that's a recursive solution. Because what we do, essentially, is the following. We basically, okay, first of all, this is Sudoku. What is the base case? This is a little harder, but there is a base case, so that's why I'm making you think about what is the possible base case. It's the case where you will stop the recursion. Okay, so when you're trying to come up with the base case, it's the case where the recursion stops. When should the recursion stop? So when you have all the numbers in. So when the puzzle is solved. So the base case is when all the numbers, when the puzzle is completely full or completely filled or completely solved. The base case is when the puzzle is completely solved. So there's 81 numbers. It's a 9 by 9 grid, right? So 81 numbers are in the puzzle and all conditions are met. Okay, so the puzzle is completely solved. That is the base case. Okay, so the recursive case is we are somewhere in the middle. So the recursive case is we are at row, let's say, n, column m. And it's not filled in. Okay, so the recursive case is we're at row n, column m, and it's not yet filled in. Okay, so what do? Okay. Step one is we go from, in order, from 1 to 9 until we find a valid number according to those 3 rules. Okay, and then we solve for what? Based on what I was just doing, having filled in the number for row n, column m, where do we go next? After filling in 8 here, where did we go next? Which is the next column or the next row? Next column. Okay, so essentially it is we solve for n, m plus 1. Now, we will have to fine-tune this, right? Why will we have to fine-tune it? We can't always call it on n comma m plus 1. If we're at the edge, we'll have to increase the row by 1. So we have to fine-tune that. But essentially, that's a rough description of our recursive solution, right? That's a rough description of it. We all good with that? Now, you say, where's the recursion? Well, what Sudoku will do is it returns true if it found a solution and false if it doesn't. If it returns false, we continue in our for loop. We move on to the next number. So if we tried it, for example, with 3 and Sudoku says failure, we move on to 4. And if we get to 9 and we're still getting failure, we return and say we failed. On the other hand, if Sudoku with n of comma m plus 1 returns true, we return true. Because if we found a valid solution for this case, we also know that 3 was valid here, so we have a valid solution. So we're returning either true or false from our recursion. False if we couldn't find a solution, true if we could. Okay? So that's what, if we go and look at his solver code, I'm going from the opposite. I'm going to solve the puzzle. So here's his puzzle solving. Okay, so first of all, he initially calls it with 0, 0 because he's going to start with the upper leftmost square. Then recursive solve is an arbitrary row and an arbitrary column. So the first thing he does is he's going to look for an empty square. There's no reason to try to solve it for a square that's already filled in. A square that's already filled in is what? Is a square that's filled in a provisional square, or is it one that was provided for us by the puzzle maker? So we're sweeping from left to right, top to bottom, right? We're going top left, top to bottom. Can we ever, in doing this, are we ever encountering a value that we already filled in? We're not. Okay, if we're going, so we first do this row, okay? When we get down to row 2, the only row we filled in was row 1, so we can't possibly have anything in row 2 yet. And as we sweep to the right, we're going from left to right, so we can't possibly have filled in anything in front of us. So if we encounter a number, it has to be one that was provided by the puzzle maker. Do we agree now with that? So if we encounter a number, it was provided by the puzzle maker, and much as we might like to do it for the difficult puzzles, we're not allowed to change them. I know that I've sometimes wanted to change the number. I know that I sometimes could swear that the puzzle maker messed it up. But in the end, I've always found that the puzzle maker did not mess it up. So what we're doing with this loop is we're looking for a grid that is equal to a dash. So we're going to keep skipping until we find something with a dash. So while the row is less than 9, because if we end up with the row being equal to 9, we're done. That's the base case. Okay, if we keep going and going and going, and eventually we can't find any more dashes, we've completely filled in the puzzle, right? And presumably, we only got to this point because all the numbers that we put into the grid were valid. Therefore, we've reached the base case, which is we solved the puzzle and it's valid. So if we ever get to r equal 9, we return 1. Okay? So that's why he's saying while r is less than 9 and the grid is not equal to a dash, we're going to increment the column. But if the column becomes 9, we've reached the edge, then we need to increment the row and set the column to 0. Okay? Now, that's only part of it. Now, when we come out of this loop, the first thing he does is he checks to see if we're done. That's one possibility. The second possibility is we now need to go from 1 to 9, and for each value, we provisionally set the grid to that value. Then we check to see, is the row valid, is the column valid, and is the panel valid. If all three checks work, we then check to see the recursive solve with r comma c. Why does that work, by the way? Because I told a white lie. Why don't I say r comma c plus 1 here? Because I certainly said it right here. Solve it for nm plus 1. But he's not doing that. He's calling r comma c. Why doesn't he just call r comma c plus 1? Bingo, Mac. So the problem is he doesn't want to have to go through the complicated logic again of checking to see whether he's at the edge of a row. So he's just going to pass the buck. He just filled in a number, right? So he knows that when he comes back up here, passing it R and C, he knows that that's no longer a dash. That was my little white lie. I got you all to agree that if we came to a number, it had to have been set by the puzzle maker. But the little white lie was that actually the first number might be a number we just filled in. But it was easier to make you accept the little white lie at the time. At any rate, since the number was filled in, he will immediately increment C and do his little boundary check. So it's okay to do what he did here. It just avoids, all he's doing is avoiding having to repeat the logic of seeing is C equal 9, and if it is, now I have to pass it R plus 1 comma 0 rather than R comma C plus 1. Okay, so if that works, so if it returns true, we return true. If it doesn't work, so if this is false, or if any of these three conditions are false, we increment I by 1 and we fill it in with the next one. And if we fall out of the loop, we reset the grid to be empty and we return 0. So if we're unsuccessful, we reset the element to a dash and we backtrack. Okay, so it's really quite simple. It's a brute force algorithm, and if we don't find a solution, we backtrack and we reset the thing to be a dash. Now, does anyone know why we don't try this incredibly ingenious solution with the Sudoku puzzles that are rated extremely difficult? Because it would take a human forever. Now, a computer with its blinding speed will make mincemeat of an extremely difficult Sudoku puzzle. So it is happy. This backtracking is also exponential in the absolute worst case. It could try literally millions of cases, which is why you don't try this approach. But the computer is perfectly happy to try several million cases, and it will do it in the blink of an eye, or at least most of these will solve in under 10 seconds. It would take a really, just like Mac, it would take a horribly pathological, extremely difficult solution for this thing to go much beyond 10 seconds. Yes?
So would a code similar to this solve the ones that are like 5 puzzles in one, or would it be a lot more complicated than this?
It would solve it, but it would take a lot longer. I think, actually, you'd have to, I'm not sure I've seen the 5 in 1, but I think it would solve the 5 in 1. Maybe you'd have to generalize it slightly, and maybe you'd have to tell me after class exactly what the 5 in 1s are. But I'm pretty sure it could solve it with backtracking. It would just, at some point, you will also overwhelm the computer with backtracking. Eventually, you could get this grid big enough that even the computer would choke. Okay, so that's why these puzzles are fun. We do it more cleverly than the computer does it. That's why we enjoy Sudoku. That's why I enjoy it. We make deductions. So the joy of Sudoku, if you were writing a computer program, is you could try to do it with what's called artificial intelligence and do it more efficiently than how I just did it with brute force. But it is nice to know that if you're absolutely stuck and you're mad and you can't get it, hey, you can just run this little Sudoku solver and it will solve it for you. So there is a few things. We have about 5 minutes left. So first of all, we have to give it a file. So the file we give it is a file with 9 lines, and the files are supposed to contain numbers from 1 to 9 or dashes. So we give it the initial, that's the initial Sudoku layout. So a dash represents an empty cell, and we input it. So obviously, here's a bad one because it has an X. Okay, what is bad with this one? Well, not so easy to say. What is wrong with it? I think it has duplicate ones in the column. So at any rate, here's bad2.txt. It has duplicate 7. Let's see. Bad3.txt has a bad column 6. So here's bad3.txt. And 0, 1, 2, 3, 4, 5, 6. You'll notice there's 2 3s. So basically, you have to do a whole bunch of error checking before you do anything. So he does that. And what do you think the fourth check is? Bad row, bad column, bad panel. So he has checks for bad panels. So at any rate, he's going through here and he has, let's see, building his solution. Let's just look at his checks first. So what he's going to do, first of all, is he's going to use, do we have it? There we go. He's going to use a vector of strings for his grid. You can, why do you think he uses a vector of strings rather than a vector of numbers? Because of the dashes. I probably would have chosen to use a vector of numbers, and what could I have replaced a dash with? 0, -1, anything that's not 1 or 9. As a result of the fact that his grid is strings, you'll notice he was doing something funny. Let's see if you can see what the funny thing was in his recursive solve. Look at his for loop for a moment. What is funny about his for loop? They're chars. So he's going from I equals char 1 to char 9. So it turns out that his he's using chars rather than integers. It's no big deal. So let's see. Initially, he sets his grid to be 9 because he has 9 lines. And all he's doing is reading in his thing 1 character at a time. So he reads them as characters. And he's simply pushing back his things 1 at a time onto, so notice he has an inner loop here. So he's essentially just pushing back onto a string. Remember, he's using, sorry, I know I'm going back and forth a lot. He's using a vector of strings. You can push back onto a string. So all he's doing is running a loop. I equals 0 to 8. And his inner loop is for j equals 0 to 8. And then he's doing grid I dot pushback. But he's pushing back onto a string. He's not using a vector of vectors, but you can push a character onto a string. So that's what he's doing in terms of reading it in. Okay? And I'll finish this up. We're out of time, and I want to spend a little bit more time on it. So I'm going to finish this up on Thursday. I'll spend probably 10 minutes finishing this up on Thursday.